Here's something that will make art purists absolutely furious. Scientists just took a laser to one of Jackson Pollock's most treasured masterpieces, and what they discovered might change everything we thought we knew about the abstract expressionist master. Picture this. Researchers pointing high-powered laser equipment at a priceless painting worth millions, all to satisfy scientific curiosity about a splash of blue paint. Sounds almost sacrilegious, doesn't it? But here's where it gets controversial. Their findings reveal that Pollock was using a pigment so rare and dangerous that it's now completely banned from production. The painting in question? Pollock's legendary No. 1A 1948, a quintessential example of his revolutionary drip and splash technique that literally redefined what art could be. Using a cutting-edge technique called laser spectroscopy, imagine using atomic-level detective work on artwork. The research team made a startling discovery. That vibrant blue that catches your eye in the painting? It's manganese blue, a pigment that's been completely discontinued for decades due to serious environmental and health hazards. But here's the part most people miss. This represents the very first confirmed instance of Pollock using this particular pigment, making this discovery historically significant beyond just scientific curiosity. Let's dive deeper into what makes this pigment so special and so dangerous. Manganese blue, scientifically known as barium manganate 6-sulfate, first emerged in the art world back in 1907 and received its official patent in 1935. For nearly a century, artists embraced this pigment for its unique turquoise-ish brilliance that simply couldn't be replicated by mixing other colors. Here's where things get interesting from a chemistry standpoint. According to Abed Haddad, an assistant conservation scientist at the Museum of Modern Art, who co-authored this groundbreaking study, there's a crucial distinction that most people don't understand between pigments and hues. A pigment is the actual chemical compound, the raw material that creates color. A hue, on the other hand, is simply what our eyes perceive as color. Think of it this way. You can mix a blue pigment with a yellow pigment to create a green hue, but you haven't actually created a green pigment. It's still two separate chemical compounds working together to trick your eye into seeing green. This is why you can still buy manganese blue in art stores today. It's not the real chemical compound, but rather a carefully crafted mixture that mimics the original's appearance. The actual chemistry behind manganese blue's mesmerizing color is fascinatingly complex. Edward Solomon, a Stanford University chemist who contributed to the research, explains that each manganese blue molecule contains a manganese ion surrounded by 4 oxide ions. When light hits these molecules, something magical happens. Electrons jump from the oxide ions to the manganese ion, absorbing light in the purple and green wavelengths while reflecting that stunning blue we see. But let's address the elephant in the room. Why was this pigment banned in the first place? By the 1990s, mounting evidence about its environmental and health risks led to its complete phase-out from commercial production. We're talking about a pigment so hazardous that entire industries abandoned it despite its irreplaceable aesthetic qualities. And this is the part most people miss. Understanding the exact chemical makeup of artwork isn't just academic navel-gazing. For art conservationists, this knowledge can literally mean the difference between preserving a masterpiece for future generations or watching it slowly deteriorate. Different pigments react uniquely to environmental factors like intense lighting, ultraviolet radiation, and humidity changes. Without knowing exactly what chemicals you're dealing with, conservation efforts can actually cause more harm than good. Haddad emphasizes this point. This knowledge can be crucial for developing effective display strategies. since many pigments are sensitive to environmental factors. Furthermore, pigment identification can help determine suitable treatment options, as some chemical conditions might react adversely with specific pigments. But here's where it gets controversial, and I want to hear your thoughts on this. Should priceless artworks be subjected to scientific analysis that could potentially cause microscopic damage? Are we prioritizing scientific curiosity over artistic preservation? Some argue that every laser pulse, every tiny sample taken for analysis irreversibly alters the original work. On the flip side, others contend that without this scientific understanding, we're essentially flying blind when it comes to conservation. How can we properly preserve something if we don't understand its fundamental composition? There's another fascinating angle to consider. What would Pollock himself think about this discovery? Would he be thrilled that future scientists were uncovering the secrets of his creative process? Or would he be horrified that his spontaneous, emotional expressions were being reduced to chemical formulas and molecular structures? The researchers concluded their study with a piece of advice that's both practical and slightly amusing. In that spirit, a note to all artists: have pity on future conservationists, and leave a record of the pigments you use in your paintings. Imagine Pollock, in the midst of his frenzied creative process, stopping to jot down detailed notes about his paint choices. It seems almost antithetical to his artistic philosophy, doesn't it? This discovery opens up so many questions about artistic intent versus scientific analysis. Are we enhancing our appreciation of Pollock's genius by understanding the molecular structure of his pigments? Or are we somehow diminishing the mystique and emotional impact of his work by reducing it to chemistry? What's your take on this? Do you think subjecting priceless artworks to scientific analysis crosses a line? Or is it a necessary step in preserving our cultural heritage for future generations? Should we be recreating dangerous pigments like manganese blue for historical accuracy? Or is the safety-first approach of using modern substitutes the right call? I'm genuinely curious about where you stand on this debate. Drop your thoughts in the comments, and let's discuss whether science and art should mix this intimately.